Hi guys, welcome to ENS181 Engineering Mathematics. In this video, we're going to discuss methods on finding a solution of a first-order differential equation, specifically an exact differential equation. So, a differential expression with mxy dx plus n of xy dy is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy defined in the region R. So a first-order differential equation of the form m of xy dx plus n of xy dy equals to 0 is said to be an exact equation if the expression on the left-hand side is an exact differential. So the value of our left-hand side of the differential equation must be an exact differential. So how are we going to identify if this one is an exact differential? So we can use this test of exactness. So the test of exactness, we get the partial derivative of m of xy with respect to y and the partial derivative of n of xy with respect to x. Then if both equation equates, then we have the exact differential. So this is the method on identifying if the given differential equation is exact or not. Since we have an exact differential equation, we can use this assumption. So we assume that the partial derivative of fxy with respect to x is equal to mxy and the partial derivative of fxy with respect to y is equal to nxy. So we can use either of these two. So we can find the value of our solution f of xy by integrating one of the equation above. So we can start by using this equation. So by integrating this one, we get function of f of xy equals to integral of mxy dx plus g of y. So we can find the value of g of y by differentiating this equation f of xy with respect to y. So we partial derivative this f of xy with respect to y. So we have partial derivative of f of xy equals to y. So this one, we differentiate this whole part of the equation with respect to y. And if you notice, this partial derivative of f of xy with respect to y, it is equal to nxy, which we assume at the beginning. So we can equate the whole equation with nxy. This gives that g prime of y is equal to nxy minus partial derivative of our integral m of xy dx with respect to y. Then, finally, we integrate the g prime of y to get the value of g of y, and then we substitute it back to the function f of xy to get the implicit solution of the differential equation and equate it to arbitrary constant c. So this one is our implicit solution for the exact differential equation. Note, we could just as well start the foregoing procedure with the assumption that the partial derivative of f of xy with respect to y equals to nxy, after integrating n with respect to y and then differentiating the result. So, if you notice, at the beginning, we start our solution with this assumption. Partial derivative of f of xy with respect to x equals to mxy. But we can also start on this second assumption on finding the solution for our differential equation. So we have here an example. We're going to find a solution of a first-order exact differential equation. So we have 2xy dx plus quantity x squared minus 1 dy equals to 0. So this one is in the differential form na. First, we identify the value of our m of xy and n of xy so that we can use the test of exactness. So based here in our example, so the value of our mxy is this one, 2xy, which is connected to dx. Then, the value of our nxy is this one, x squared minus 1, which is connected to our dy. So after identifying the value of mxy and nxy, we are going to check the test of exactness. So we have to get the partial derivative of mxy with respect to y. It should be equal to partial derivative of nxy with respect to x. So we are going to differentiate this equation with respect to y. So the derivative of 2xy with respect to y is 2x. Then we're going to differentiate this equation with respect to x. So the derivative of x squared minus 1 with respect to x is 2x. So by the test of exactness, we found out that the differential of our equations are exact. So after the test of exactness, we can use the assumption partial derivative of f of xy with respect to x equals to m of xy, or partial derivative of f of xy with respect to y equals to n of xy. So we can use first this one. So to find the value of f of xy, we integrate this equation. Integral of mxy dx. So we integrate this one. We have value of our f of xy. Then we substitute the value of our mxy, which is 2xy dx. So we have integral of 2xy dx is just equal to x squared y plus g of y. Now, to get the value of g of y, we can partial derivative this whole equation with respect to y. So, partial derivative of fxy with respect to y, partial derivative of x squared y plus g of y with respect to y. So if you notice, this partial derivative of f of xy with respect to y is this second assumption. So we can equate this one with n of xy. So partial derivative of this one will have x squared plus g prime of y. Then we equate the nxy natin, we have x squared minus 1. X squared minus 1. So, rearranging this equation, cancel si x squared, we have g prime of y equals to negative 1. So, to get the value of g of y, we integrate both sides of the equation. So we have partial derivative of g of y with respect to y equals to negative 1. So integral of g of y equals to integral of negative 1 dy. So our g of y now is equal to negative y. So we substitute it back to our function f of xy. to get the value of our solution. So the solution now is x squared y plus our g of y is equal to negative y equals to c, since we are doing integration. So inisa lang natin at the end of our solution ang ating constant of integration. So finalizing this one, our implicit solution is x squared y minus y equals to c. So this is our implicit solution for the first order exact differential equation 2xy dx plus x squared minus y dy. So we have another example here. We're going to solve the differential equation dy over dx equals to xy squared minus cosine x sine x over y times the quantity 1 minus x squared with the initial condition of y of 0 equals to 2. So we have an initial value problem. So if you notice, our differential equation is not in the differential form. So we have to rearrange this equation so that it is easy for us to identify the value of our mxy and nxy. So we have y times 1 minus x squared dy equals to xy squared minus cosine x sine x dx. We transfer this on the left hand side. We get cosine x sine x minus xy squared dx plus y quantity 1 minus x squared dy equals to 0. So now, our differential equation is in the differential form. So based on this form, we can identify now the value of our mx and nxy. So this one is our mxy and this one is our nxy. So we're going to identify is this one is an exact differential equation. So by the test of exactness. So partial derivative of mxy with respect to y must equal to partial derivative of nxy with respect to x. So partial derivative of mxy with respect to y, we get negative 2xy. Then partial derivative of nxy with respect to x, we have negative 2xy also. So by the test of exactness, we have an exact differential equation. So we can now use our assumption, partial derivative of f of x with respect to x equals to m of xy and partial derivative of f of x y with respect to y is equal to n of xy. So in the previous example, we start with this assumption. So in this example, we're going to start with our second assumption. So partial derivative of f of xy with respect to y equals to nxy. So the value of nxy natin is y times 1 minus x squared. Now, to get the value of f of xy, we integrate both sides of our equation. So, we have f of xy equals to y times 1 minus x squared dy. So integral both sides. We have f of xy is equal to, so integral ng y, quantity 1 minus x squared dy, we have y squared over 2 times 1 minus x squared plus h of x. Now, to get the value of our h of x, we're going to differentiate partially this f of xy with respect to x so that we can use this first assumption. So we have partial derivative of f of xy with respect to x. So partial derivative rin natin ang right hand side of our equation, y squared over 2 times 1 minus x squared plus h of x with respect to x. Partial derivative of f of xy with respect to x is equal to y squared times negative x plus h prime of x. So continuation, we have the partial derivative of f of xy with respect to x equals to negative x y squared plus h prime of x. And if you notice, this partial derivative of f of xy with respect to x is just equal to our mxy, which is the first assumption that we do at the beginning. So we can equate this one to our mxy. So our mxy is cosine x sine x minus xy squared. So now we simplify this equation. So cancel si negative x y squared at ang matitira na lang is h prime of x equals to cosine x sine x. So we transform this h prime of x to its equivalent Leibniz notation. We have dh of x over d of x equals to cosine x sine x. Then we transpose dx to the right hand side of our equation. We have dh of x equals to cosine x sine x dx. Then we integrate both sides so that we can get the value of our h of x. So we have h of x on the left hand side. Then the integral of cosine x sine x, we let u equals to cosine x and du is our negative sine x dx. Then we substitute this back to our differential equation. So first we rearrange the right hand side of our integration. You can write negative integral of cosine x times negative sine x dx. So now we can substitute u and du to our integral. So we have negative integral of u du. So our h of x is equal to negative integral of u du is u squared over 2. Then we substitute back our u. We have negative 1/2 cosine squared x. So the value of our h of x is this one, negative 1/2 cosine squared x. Then we substitute it back to our f of x. We have f of xy equals to y squared over 2 times 1 minus x squared plus the value of our h of x is negative 1/2 cosine squared x. So we can equate this whole equation with arbitrary constant c. So we have y squared over 2 times 1 minus x squared minus 1/2 cosine squared x equals to c. So we simplify this equation, we multiply it by 2. So we have y squared 1 minus x squared minus cosine squared x equals to c. Since constant multiplied by a constant is just equal to constant. So to find the value of our arbitrary constant c, we apply our initial condition. So the value of y is 2 and the value of our x is 0. So we have 1 minus 0 minus cosine squared 0 equals to c. So cosine squared 0 is equals to 1. Then 2 squared equals to 4. So 4 minus 1 equals to c. So our c is just equal to 3. So our implicit solution now will be y squared 1 minus x squared minus cosine squared x equals to 3. So this is the solution for the initial value problem of an exact differential equation dy over dx equals to xy squared minus cosine x sine x over 1 times the quantity 1 minus x squared. So now we have practice quiz for exact first order ODE. So I want you to pause this video and try find the solution of the differential equations given. So that's it for the first order exact differential equation. So I hope you learned from this video. So the next topic will be not exact ordinary differential equation. See you on the next discussion.